Hello again. So in the previous video on improper integrals, we looked at a couple examples. We looked at the example where you have, say, an integral from 1 to infinity of x to the negative 2 dx, and we looked at the integral from 1 to infinity of x to the negative 1/2 dx. And we saw that one of these converged to 1, and one of them diverged to infinity. And in both cases, we're looking at, 1 over x squared, which does this maybe, and 1 over root x, which does this. So 1 over root x doesn't get to the axis fast enough. Remember that 1 over x squared, x to the negative 2, same thing. 1 over root x, x to the negative 1/2, same thing. But this does not get towards the x-axis fast enough, and thus the area underneath it is infinite, while 1 over x squared does get to the axis quite quickly, and therefore the area actually converges to 1. In other words, you're adding such tiny, 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 tiny pieces of area, even though you're adding infinitely many of them, that it just converges to a number. Here, the areas that you're adding, those little slices of areas down here, do not get small enough fast enough, and so you just end up with this infinite amount. But now what we'd like to look at is what happens when, say, you look at a different sort of problem. So what we could call this is maybe infinite integrands. And so infinite integrands would be when the function you're finding the area underneath has issues. So maybe heads towards infinity. So now instead of the x value, instead of going towards infinity this direction, we're going up maybe usually a vertical asymptote type of issue. So let's say we had the integral from 0 to 1 of 1 over root x dx. So thinking about 1 over root x, what you want to watch out for is this thing undefined at 0 or 1 or somewhere in between? Well, 1 over root x is undefined at x equals 0. And in fact, it has a vertical asymptote there. So we can't just simply treat this as normal. These ones are a little bit trickier because here we can see the infinity, so we know we have to change that to a letter and take the limit. But here we wouldn't necessarily see that unless we're thinking on our toes. So we got to say, wait a second, I can't just plug 0 in here. That doesn't make sense. I'm really looking for the area from 0 to 1, but I'm not sure whether that area in there is infinite or not. So I gotta be careful when I'm thinking about this. So again, find that limit that's the problem, or limit, I say limit as in limits of integration, and change it to a letter and take the limit as the letter approaches that limit. I'm using limit for two different things here, which is pretty confusing. So maybe I should say the bounds of the integral, and we're going to take the limit as the letter approaches that bound. So this is going to become the limit as a approaches 0 from the right of the integral from a to 1 of x to the negative 1/2 dx. So I know that I'm approaching from the right because I can't plug in negative numbers here. And also, this is my region right here from 0 to 1. So the limit I need to be approaching from the right. If I were approaching from the left, I'd be over here, and I don't want to be over in that second quadrant. So this is now going to give me the limit as a approaches 0 from the right. And now I just need to find this normally of we found this antiderivative before, but it's x to the 1/2 divided by 1/2 evaluated between a and 1. That's the limit as a approaches 0 from the right of 2 root x between a and 1. That is the limit as a approaches 0 from the right of 2 minus 2 root a. And now I can plug in 0, or I need to figure out what this limit is. But if I plug 0 in here from the right, this is just approaching 0. So that's no problem. So this just actually equals 2. So what we could say is the integral converges. And furthermore, we can say the integral converges to 2. So interesting to think about 1 over root x. It does not approach the x-axis quickly, but it does approach the y-axis quickly, while 1 over x squared is sort of like the inverse in a sense. It approaches the x-axis very quickly, but not the y-axis. So let's look at one more example of this type of problem. Let's take, for instance, the integral from -1 to 2 of x to the -4 dx. This is the same as the integral from -1 to 2 of 1 over x to the 4th dx. So 1 over x to the 4th is a volcano-looking thing. It looks like this. Now notice you can plug -1 into that, no problem. And you can also plug 2 into that, no problem. But you have to have the knowledge to say, wait a second, this is undefined at 0, and 0 is between -1 and 2. So this is not a trivial thing, because I'm going from -1 to 2, so I want to know if this area right here is infinite or whether it is finite. So to do that, I need to actually break this up into 2 integrals because I need to have one of my limits be that problem area. So I'm going to say that this should be the same as the integral from -1 to 0 of x to the -4th dx, plus the integral from 0 to 2 of x to the -4th dx. So I have just gone now from -1 to 0 and then 0 to 2. So I'm finding this integral and this integral separately. Now I need to change my problem bound to a letter and take the limit. So this should give me the limit as a approaches 0 from the left this time of the integral from -1 to a of x to the -4th dx, plus the limit as, let's say, c approaches 0 from the right of the integral from c to 2 of x to the -4th dx. So limit from the left, because I'm going from -1 to a, so I'm approaching from the left. From the right, because I'm going from c to 2. So I'm not coming from this side, I'm coming from this side. So that's why I'm coming from the right on this one. Okay, now I can find these and say, great, this is equal to, so I'm going to find this integral right here. The limit as a approaches 0 from the left, this should be x to the -3 divided by -3 evaluated between -1 and a, plus the limit as c approaches 0 from the right of x to the -3 over -3 evaluated between c and 2. That should be the limit as a approaches 0 from the left of, 1 over -3a to the a cubed, right, because a to the -3 is a cubed, minus, it's going to be 1 over -3 times -1, plus now the limit as c approaches 0 from the right, plugging in 2, I get 1 over -3 times 2 cubed, which is 8, minus 1 over -3 times c cubed. So I know that's all kind of a lot, but We're just plugging those numbers in, basically. Now, as a approaches 0 from the left, this thing right here is heading towards 1 over 0. That's bad. That's very bad. In fact, that means that it's heading towards infinity or negative infinity. This doesn't really matter because this thing is blowing up. So if I approach 0 from the left, I'm plugging in small negative numbers. So this is a negative cube times a negative. So this thing right here is heading towards infinity, okay, which makes sense from the picture. That should not be negative infinity. That should be infinity. And then at that point, I don't even really care about this because if one side of my integral goes to infinity, it doesn't really matter what the other one does, but I'm sure it goes towards infinity as well. And as C approaches 0 from the right, this is going towards negative infinity. With the negative, it's also going towards infinity. So the whole thing is tending towards infinity, which tells me the integral diverges in the worst possible way towards infinity. So these are the types of integrals that involve infinite integrands, and they can be a little bit tricky, so you just got to be careful about what values make your function undefined.